Okay, good afternoon. May I ask, is YouTube still working? I heard that it should... Ну, давайте по-русски. Сейчас YouTube работает? Вы не проверяли?
Да, вроде, да.
Ну, ладно, тогда я пока оставлю как есть YouTube. Okay, so today we are going to use a text. It's actually a textbook. Okay, I'm going now to share my screen. Так. Okay, now I'm sharing my screen. Okay, I don't quite remember. I already mentioned it. I think it was in syllabus at least. It's called Logic and Proof by Jeremy Avigad and other people. Jeremy Avigad is a professor of Carnegie Mellon University. So it's a textbook. There is also some general things about proofs, but I think it's actually less than I presented that we already covered in this course. But then there are more specific chapters on propositional logic and on natural deduction for propositional logic. And then there is a chapter that's interesting. I think we are not going. I decided not to include it in that course. Lean is a proof assistant, and proof assistants are computer software. No, they are similar to, say, languages, programming languages, and the idea is that in proof assistant, in particular in Lean, you encode a proof as an algorithm, as a code, and the idea is that then its code becomes checkable, computer checkable. So the idea is that you have a mathematical proof written in such a algorithmic form that can be checked with computer. And that, of course, becomes important when proofs are complicated. So you can run it on computer, and computer would tell you if it runs correctly or not. And so you may, in explicit form, see your assumption, your deduction rules of deduction, and say your conclusion, which is actually a particular theorem that you want to prove. And this whole process, you think about it as a automated in the sense of being implemented on computer mathematical proof. Yes, and that should be actually distinguished from idea to find a proof with computer. So in such a situation, computer does not find the proof, so it's still up to a human, to a mathematician to invent this proof, to find that proof. However, it's presented in this computer checkable form. Okay, and proof search, it's another thing, and that's actually an area in mathematics and computer science, which is rather actively is now developing. It's still not very common, so it's not common for, say, mathematician to encode mathematical proofs in such a form. However, it's something that develops, but still I think this course that we have now, it's rather preparation. So I decided to skip these parts. Even some of you who are interested may look into, and then we can probably do something together. Maybe next spring, actually, I was planned to make another course on this computer assisted proofs, as it's also often called in English. Okay. So, okay, now everybody see the screen. I also I can send actually this file in the chat now. Okay, so you can download it, and then I also do it again via this Microsoft system, and so you would have this text. Wait, I just try my computer. Sorry, so okay. Yeah, this is a file. So please just download it and save it on your computer. Now, okay, is it sent?
Yes.
Good. Okay, so you may also look at. Yeah. It's also called interactive theorem proving, this work with proof assistant, because it's again, it's kind of joint work of human mathematician with computer. So it's not the idea that computer somehow replaces a human. I should say I'm rather skeptical about this idea, and not because of computers are not powerful enough, but somehow I don't think it's a good idea to replace human with computer. It's I believe it's better idea to to extend humans' capacity with computer. So computer is an instrument rather than some independent actor. No, at least this is my, we may probably talk about this, and I know this controversial point, but that's at least my way to think about computer, that it's somehow broadens human capacities rather than replaces humans, at least in such things as mathematics. Okay. Yeah, so you may probably read. Look, maybe as a warm-up, we may also look into this exercise. It's on page 7. It's supposed to, it's a problem which is not really mathematical problem. It's rather kind of logical problem. It's about crime, to find a killer, something like this. And I would say it's not typical mathematical problem, right? However, I think it's included here to illustrate how this system of so-called natural deduction. Natural deduction is just a name for particular deductive system. So maybe I just recall you very briefly what we discussed last week and maybe one before the last. So we discussed some generalities about logic, okay? And actually we were thinking about logic as a system of rules, rules for reasoning. So we were thinking about logic as some discipline of reasoning, of correct reasoning. And so we are going to have certain rules. And the idea is that if your reasoning follows those rules, it is correct reasoning, and otherwise it's erroneous reasoning. And then we are going, and so natural deduction is actually a name for a particular set of such rules. Yeah, and remember we also discussed that in logic we distinguish between semantics and syntax, right? And syntax is about meaning, what certain expressions, terms, symbols, what they mean. This is semantics. And syntax is just how they look like formally. So the idea is that we may just look at the symbols and just for purpose of its analysis, if you like, of its proper analysis, we somehow abstract away from what they mean, right? They just look how they look like, right? And look like means what kind of symbols they involve, right? What are rules of combining those symbols, say, into words, and words into certain expressions, and the last but not least, what are rules of obtaining new expressions from some given expressions, right? And that's how we think about reasoning. So in the setting, we think about reasoning a bit linguistically, say, right? So we analyze how we reason just looking into linguistic means by which we reason. And even more specifically, we don't look just into natural language, because many things just go on in natural language, of course, it's absolutely indispensable, just like my lecture now in natural language, right, in English. However, in logic, we also apply elements of, say, artificial language, if you like, right, which symbolic language. And that also brings us closer to mathematics. It's something that you're familiar with from your mathematical class in school, when you solve equations and things like this. Okay. So this natural deduction, yeah, I'll probably, when we come to that, I probably give a bit more historical detail. And now it's just example of reasoning. Example of reasoning. So first we trying to solve it. It's going to be a problem, not mathematical, but still a problem. We are going to solve it. And if we cannot really solve it, we look into solution, which actually follows. And then we see that this solution and this reasoning is really very well captured or expressed by rules which we are just going to study just after. So if you like, it's some sort of motivation for this natural deduction that I'm going to introduce. Yeah, you may ask me, and I think that would be a relevant question, why you wouldn't give us really mathematical proof, right? We already had some example of mathematical proofs, and why you give some stupid example about man, woman, victim, killer, Alice, children, etc. Why not mathematical example? And actually, answer is that I already mentioned it. It doesn't work as smoothly with really mathematical examples. So I would say there is some true difficulty here, kind of hidden. But anyway, let's just look into this problem and see. Yeah. So here is the problem. So Alice's husband, second, their son, their daughter, so it's a couple and 2 children, and Alice's brother, so it's an uncle, right, of these kids, were involved in a murder. Well, you know, it's just for the sake of example. One of the 5 killed one of the other 4. No, it's like you know, Sherlock Holmes kind of thing. And we now should reason. We have some facts and should deduce who is the killer. So the following facts refer to the 5 people mentioned. Fact number 1: a man and a woman. Okay, and we don't know which, right? So just a man and woman, and we're supposed to guess that Alice is a woman and daughter is a woman, right? Or maybe a man and a woman were together in a bar at the time of the murder. That's first thing. Second fact: the victim, one who was murdered, and the killer were together on a beach at the time of the murder. Okay. Fact number 3: one of Alice's 2 children, so it's either son, either daughter, was alone at the time of the murder. Fact number 4: Alice and her husband were not together at the time of the murder. Fact number 5: the victim's twin was not the killer. Somehow I missed it about twins. Who was a twin? No, okay, we just should. So this
Alice and her brother are twins?
Maybe, or it could be her kids could be twins.
Oh, yeah.
Maybe.
Also.
Okay. Yeah. The victim twin was not the killer. And the killer was younger than the victim. No, so it should be sufficient to deduce who is the killer. No, maybe. I must confess I'm not very good in this kind of puzzles. So maybe I just leave you for 5 minutes, okay? If you don't mind. You try to think. Okay, you can look into the book, of course, but try guess yourself. And if not, look into the book. Yeah, but just for one thing, you see, there could be more than one reasoning, of course, right? So if this is the case, and it should be the case, unless these authors really want to, to trick on us, it should be deducible. Okay, let's assume it is deducible. But then, of course, could be different deductions, right? You may have some versions of reasoning, and it's maybe more than one way of reasoning that just gives us the right answer. Okay. Okay. So let me just leave you for 5 minutes. I come back. Perhaps someone is ready.
I looked at the solution. I was wrong, so I'm not gonna say anything about it.
I see. No, I must confess, it's not kind of thing I can easily figure out in my mind. So probably we are just going to look into solution, but maybe some of you are smarter than I am. And yeah, there is also a hint, you see. First, find the locations of two pairs of people at the time of the murder.
So it's the bar and the beach.
Yes. And then determine who the killer and who the victim were, so that no condition is contradicted. Yeah, so so two people were on the beach, all right, and then those were victim and the killer, and two other people were in a bar. Okay. And if killer was younger than the victim, how we know who? No, we assume that this kid's son and daughter, they're younger than.
Yeah, I also wanted to say that I suppose that the killer was one of the Alice kids because they're younger.
No, I think this condition is like it refers to the words no condition is contradicted. So if it's not necessarily are going to be the kids, but if we're going to find someone and we realize that killer is so the victim is not children is what I wanted to say.
Right, absolutely, you're right. Oh. On the other hand, we don't know about Alice's brother, right? He could be younger than Alice, and theoretically he could be even younger than, say, son or daughter. We don't know. Yeah. No, okay, let's maybe look into solution.
I just realized that from the this statement, we can assume that the victim has a twin. So Alice's husband cannot be the victim because he doesn't have a twin as we see.
Right. So husband. Okay, let me probably I open my board. Sorry. And then we can write at least certain things, right? And then yeah, the problem is I cannot share at the same time a board and this PDF. Yeah.
Well, you downloaded it, so.
Okay, yes, probably I can just. Okay, so what you are saying, let me just write it and then we'll see if it's correct or not correct. That so we have Alice. Alice, her husband. Okay, I just write husband. then was Alice's brother somehow involved, right? No, let me call him uncle. And then we have son of Alice and her husband and daughter. Okay, so 5 persons. Okay. So we know victim has a twin. Is correct?
Yes.
Okay. So we already deduced something, at least, right, from this condition. We don't yet deduce who is a victim, but still deduce something. Victim has a
Uncle
twin.
is a victim because he has a twin and he is older than the killer.
Yeah, say it again, please.
I guess uncle is a victim because he have a twin and he's older than the killer.
Uh-huh. Okay, let's that's I think easy because this say hypothesis, and so hypothesis is uncle is a killer, right? Is the
No,
killer
victim.
is the victim. Okay. Is the victim. Okay, and this I think we may check. So the idea is that if this hypothesis or statement that uncle is a victim, if it's compatible with all those conditions, then no, actually that does mean that he is the victim, right? Because actually what we assume is that the pair of killer and victim should be compatible and uniquely defined. So, but if we only specify victim or only the killer, right, there should be there could be different hypotheses which are compatible. But let's at least try this. So
It is 100% that the victim is either Alice's husband or uncle. It's not like it's a effect. We can say that, at least. That it's 3 of them could be the victims, not 5.
yeah, maybe that could be strategy indeed. We first we're trying to understand who can be victim and who can be killer, right? So we may probably rule out certain. For example, we rule out that son and daughter are killers, right? Because then all other people are older, and we are told that it couldn't be. Except we don't really know about this uncle. But let's assume he's older. Otherwise, it's. So let's say uncle is a victim. Yeah, these people could be together. Why not? Okay, that means uncle. Okay. Okay, and that means that Alice was not so Alice could be his twin of uncle, right? And he could be not the killer. And yeah, so it's at least we may say it's possible. Okay, maybe we may try that he's the victim and who is the killer, just like a hypothesis, and then we try this hypothesis and see if it goes through or doesn't go through. So what is your favorite suspect?
Well, I don't actually think that uncle is the victim. Be-
Why?
Because, okay, if he is the victim, then he should have been at the beach at the time of the murder.
Right.
And because of that, Alice, she's his twin, so she couldn't be at the beach because we know that the twin is not the killer.
Uh-huh.
Therefore, Alice should have been at the bar.
Uh-huh.
But because we know that the victim has a twin, we can definitely say that the husband is not the victim. He doesn't have a twin. And from that, we can assume that the husband, at the time when everything happened,
May I just correct that? Assume actually means that we just take something for granted, either hypothetically or for some other reasons. But
we
if
can
you say
conclude.
therefore, it should be assumed, right? Therefore, something is the case. No, it's just linguistic. Okay.
Okay. So we can say that we can conclude that he was in the bar, well, because he's not the victim, and he couldn't be at the beach. And one of the statements says that Alice and her husband were not together at the time of the murder. So Alice couldn't be in the bar, and because of that, we conclude that she was at the beach. So probably she was the victim.
Yeah, it looks. Yeah, right, exactly. So she cannot be. Yeah, because if uncle would be right. Yeah. I think that's right. So we disqualify this hypothesis. Yeah. So let's just see what. Okay, I probably will not repeat all you said, but what is a general strategy, right? So you take certain hypothesis, uncle is the victim, and then you follow certain steps, and after all, you derive contradiction. So I'm going to remember I use this horizontal bars for inference, or syntactically speaking, derivation. Right. So we reason, and then we use, of course, these facts. Those facts we can describe them as assumptions, because that's something given. And more technically, assumption is everything which is above the bar. And so it consists of those so-called facts, kind of given assumptions, and also something that you derived earlier from some other assumptions, right? And finally, you see, you derived contradiction. So we derived something that contradicted, again, another assumption that Alice and her husband were not in the bar, right? So it was in the bar and it was not in the bar, and that's a contradiction. And on the basis of this contradiction, we are saying that, okay, something we started from, that this hypothesis is uncle is a victim, is actually false. And that's actually going to be one of our rules of reasoning. So if we start with something and we proceed in this way and we come to a contradiction, then we actually we infer that our hypothesis was false. That's not just illustration how it works. But okay, let's what is, oops, sorry. Yeah, so he cannot be. So you want to try Alice, that Alice was a victim, right?
And who's the killer then?
Yeah, good
You have-
question. I don't know. Sorry, but I did.
So-
I did this last year, but I really forgot. I can't remember.
It means if Alice is the victim,
Mhm.
it means that the daughter was in the bar and the son was
Yes.
alone. Mm,
Mhm.
So the Mhm.
Okay, let me. Okay, let me try.
So it means that
Alice.
Alice was in at the beach with who? Not with the daughter.
No, again, we may just. I think that's basic idea how we reason, right? So we try different versions, and there is a lot of combinations actually. If we have 5 people, it's a combinatorial question how we may take 2 things. We may actually calculate, I think it's going to be, it's called combination from 5 people of 2 things, and that's I think it's equal 5 factorial. Do you know what's factorial? 2 factorial and 3 factorial, like this. 5 factorial is 1 times 2 times 3 times 4 times 5, and 2 factorial is just and we want to divide it by 1 times 2, it's 2 factorial, and also 3 factorial. 5 minus 3, 3, it's still a lot. It's okay, this is the same. Yeah, so we have actually 10 different no, sorry, I shouldn't write this one. Right, so it's be 20, you see. It's 20 different pairs who is victim, possible victim, and who is possible. And this is a lot, right? To just to check all 20 is boring. Yeah, but let's just check Alice, and if it doesn't
Alice,
work.
I don't think that Alice is the victim here.
Yeah, why you don't think so?
Because, okay, I'll try to explain because I had it in my head right now. So if Alice is the victim, then the daughter was in the bar, and the daughter was in the bar with a man.
Okay,
So
let me write it down. Sorry, because
Okay.
I cannot just reason as quickly as you do. Okay, so now you want to prove negative fact that Alice is
Yes.
not. Okay. So again, the same scheme, right? So we are saying Alice is a victim, is the victim, and then we derive a contradiction. So you claim that you can derive a contradiction. Okay.
Okay, so if Alice is the victim, then she was in the bar. Or no, she was on a beach with someone. And
then, yeah, Alice is or was okay on a beach, right?
yeah.
Beach.
Then we have the first condition that the man and the woman were in a bar. It means that the daughter was definitely in the bar with a man, with some kind of man.
Alice is on a beach, and then daughter is in a bar.
Yeah.
With a man.
Yes. So this man cannot be a son because one of Alice's two children was alone at the time of the murder. And it cannot be Alice's brother because we have the fourth condition, Alice and her husband were not together. So if Alice and her husband were not together, that means that her husband and daughter were in the bar together. So the father and the daughter were in the bar.
Husband.
Okay, so again, we have Alice and her husband were not together at the time of murder. We have two people in the bar and two people on the beach. So if Alice were on the beach, then the husband were in the bar with the...
Okay, so again, contradiction, right?
No, we have, no. The husband and the daughter were in the bar. The son was alone and Alice were with her brother on a beach. It means that her brother is the killer. But it says the victim's twin was not the killer. I don't know if it's about Alice or not.
No, okay, let's look solution. Or maybe someone is more patient than I am.
Now I realize that Alice's husband still could be on a beach because he could be the killer. Well,
no, it says Alice and her husband were not together.
Yes. I understand that Alice is definitely not the victim. I'm just confused right now because her husband cannot be the victim also. But I just see that, before I stated that he couldn't be on a beach. Now I realize that he could, but just not as a victim, but as a killer.
Maybe husband killed the uncle.
Yes.
We don't know if he's older or younger, or it doesn't matter.
Yeah, that could be. At least it's compatible, right? No, let's try this. Okay. So so husband killed the uncle. Okay. So let's see if it doesn't contradict anything, then it's the case. No, okay. Before we do that, I say kind of moral. You see what is actually going on. The reasoning by itself, as it is, right? It does actually help us to make a right guess, right? So what we can do is to make the guess and then go through conditions, right? And then reason. And we either refute this guess or hypothesis, or we prove it. And the idea is, yes, that if we don't refute it, then we prove it. So if it's compatible with all conditions, of course, there is a further actually difficulty. We actually should, to make it a real proof, we should actually have an evidence or show that all other possibilities actually fail, right? That is the only, because if we only find, say, a pair of victim and killer, which is compatible with all those conditions, it's not enough for a proof, right? Because we can also say it is a suspect. So, so in order to really to make it into a proof, we should rule out all other possibilities. That's I think that's important, right? Otherwise, we just say, yes, yeah, that works out. So this is the killer, that's victim. And this is, of course, would be a logical mistake, which is an important mistake in that case, right? Because it only may work if all other possibilities are really ruled out. yeah, that's. But let's at least try this, and then we can. So now we explore
sorry.
possibility. Okay.
Can we just start not with the killing case, but as it was hinted, with who was in the bar? Because I think it
Yeah.
was the easiest way to figure out people.
Yeah.
And then out of this, we can figure out who was at the beach. And then
Yeah.
we have smaller possibilities of what can be actually,
Okay.
who can be the
Let's
killer. or who
do this. Let's do the. Yeah. That's exactly what this scheme tells us. So instead of just trying to answer the questions immediately, we think about some other thing first, and then. Yeah. Okay.
Yeah, so it was stated that a man and a woman were together in a bar.
Mhm.
So, and we know that Alice and her husband weren't together. So we have the possibility of it being either Alice and her brother.
Okay. Let's me. Okay, so that's I say it's kind of, it could be the case, but it's wrong strategy. So now we are trying who was in the bar, war in the bar. Yeah, and here we may have less possibility. So please tell again.
Yeah, so in the bar, it was either Alice and her brother.
Alice and, okay, we call it uncle.
Or uncle, yeah. Or
Mhm.
it was a husband and a daughter.
Yeah, and why? So why
No,
other?
can I please interrupt? It can either be Alice and her son. No?
Yeah, Alice and her son, I'm sorry.
Mhm.
I forgot about it.
Alice, son. And why it couldn't be Alice and daughter, for example?
Because there were man and a woman.
Right. Okay.
So we only have a man and a woman in this case. So out of this, we can rule out who could be potentially at the beach. So
In the bar.
yeah, it was the bar.
Yeah.
And okay, if Alice and her or Alice and uncle were at the bar, then on the beach there was a husband.
Okay. Yeah. So if it's Alice and uncle, then it's what you saying?
The husband was at the beach.
Husband and
okay, and either son or daughter.
son, okay, daughter. Okay. If it was husband and daughter.
Okay, if husband and daughter were at the bar, then Alice was at the beach. Okay. 1 second.
With
so
with
we
uncle?
know that the victim's twin was not the killer, so it probably wouldn't be uncle, so it would be the son. Or daughter again. No, if yeah, the son, because the
son,
daughter was at the bar, yeah. But it couldn't be the son because one of the children was alone.
Was alone. Right,
Yeah.
so it couldn't be.
Yeah, then probably Alice and uncle at the beach. But yeah, the killer was not the victim's twin was not the killer, so the pair of Alice and uncle isn't possible either, because one of them would be the killer, because the killer is at the beach. So this possibility is just incorrect.
Yeah, so we disqualified.
Yes.
Okay.
So we have Alice and son at the bar. Then at the beach, it would be her husband. And uncle. Because the son is at the bar and the daughter would be alone.
Alone.
So
yeah. So once again, okay, so what we actually achieved, we ruled out this possibility, and here actually we have two possibilities, right? So it's Alice uncle in the bar,
or husband and son, or daughter, because we don't know, there are like two possibilities. So probably we should start with the last one, because it's the most like
sorry,
obvious.
I guess we've missed one of the pair. Like in the bar, there could be the daughter and the uncle.
In the bar, daughter and uncle.
Yes,
but at the beach would be husband and Alice.
Oh,
yeah, and
they cannot
not...
be together.
Yeah, they cannot be together.
Okay. Sorry.
Yeah, it looks like we are actually close.
Yeah, maybe we should start with the last one, Alice and son, husband and uncle. Because I think it's like the most like easiest. Like,
okay, let's start. No, so question is whether we may choose between these possibilities, or if we cannot, we don't have really solution. But it should be possible actually to choose, I guess.
Okay, let me think then.
Let's see. The killer was younger than the victim. Okay, that's something that's not impossible in this last case. And
I think that the man, it's like it's always going to be a man, either a killer or a victim. Don't know
why. Twin was not the killer. So in first version, husband would kill either son or daughter, right?
No, the killer was younger than the victim.
So the son or daughter is the killer and husband is the victim.
All right. Yeah, I was younger than. Yeah. Alice, uncle. Let's.
So the victim cannot be the daughter, I think. 100. I don't think it's the children.
Why?
Because if the killer is one of the children, for example, if one second.
Actually, since they're talking about victim's twin, right? I think we should assume that victim has a twin, just among those. Yeah, I think it's this condition 5 is actually a little bit ambiguous because either we should assume that, and that's I think is a correct reading, that victim has a twin, and this twin is just one of those 5 people, right? It does not refer to
yeah. So if
someone
we
else.
figure out that like the victim has a twin, then the first possibility is also couldn't be possible because the son or daughter could be the killer.
But I would say it's a bit ambiguous because of course we can simply read that there is twin elsewhere, which has nothing to do. Yeah, but I think we should read it that way. Yeah, let's try to read it that way.
Yeah, and the only possibility is that like at the beach were husband and uncle.
Yeah.
Yeah, and uncle is the victim.
Uncle is the victim. Yeah. No, looks like this. Okay,
because the victim's twin was not the killer.
Victims. Right. And sorry, and if but if uncle is a killer, if uncle killed husband, what's wrong with that?
Actually, the 6th one is like the killer was younger than the victim. Like, who is the younger, husband or uncle? Is just unclear for me.
Yeah, we don't know.
Didn't we agree to think that the victim has a twin and the husband does not have a twin?
Let's agree that victim has a twin and just among those 5 people. And that, of course, also rules out some possibilities, right? So who may have a twin? So kids could be twins, but that's irrelevant already, right? We say so. It's only possible that victim then is an uncle, right? And husband is a killer, right?
Yes. Then
yeah.
Then who is? Then Alice and the son are in the bar, and the daughter is alone.
Yeah.
And the victim's twin is not a killer.
So
nothing contradicts.
In the bar. So again, we should not simply say show that it does contradict anything, but we should also show that anything else contradicts, that all other versions. No, this is that we more or less show, right? So we had this 3 possible versions and we ruled it out one after another. And the daughter are in the bar, is alone. And so finally, husband killed uncle, right? Husband. No, let's check what they say. Killed uncle. Yeah, let's see what they say. Maybe we are wholly wrong. Okay. Solution. If you have worked on the puzzle, you may have noticed few things. First, it is helpful to draw a diagram. Yeah, we're a bit lazy. Yeah, that's true, by the way. This diagram would be better. The number of characters, location, and attributes is finite, so there is only finitely many possible state of affairs. Yeah, but still a lot. calculated how many pairs of victim, and there are 20, and that's already a lot. The numbers are also small enough, so that systematic search for all the possibilities, though tedious, will eventually get you to the right answer. This is a special feature of logic puzzles like this. You wouldn't expect to show, for example, that every even number greater than 2 can be written as the sum of primes. Okay, that's just, they refer to this Goldbach conjecture, remember. Another thing that you may have noticed is that the question seems to presuppose that there is unique answer. Yeah, that we discussed, which is to say, over all the state of affair, that means the list of conditions, there is only one person who can possibly be the killer. A priori, without that assumption, there is a difference between finding some person who could have been the victim and showing that that person had to be the victim. In other words, there is a difference between exhibiting some state of affairs that meets the criteria and demonstrating conclusively that no other solution is possible. The published, you see, it's taken from some other book. That's why they also comment here. The published solution in the book not only produces a state of affairs that meets the criterion, but at the same time proves that this is the only one state of affairs that does so. It is quoted below in full. Okay, let's. Okay, from 1, 2, and 3, and this is 1, 2, and 3. The roles of the 5 people were as follows: man and woman in the bar, killer and victim on the beach, and child alone. You see, by the way, it's interesting also mathematically, if you like, because you see, they take a little bit different strategy than we did. Instead of just naming these people by like constant names, like as we did, Alice, husband, uncle, they just they use the sort of names like man and woman, right? And it could be different options for being a man here and woman. Okay. Then from 4, what follows that either Alice's husband was in the bar and Alice was on the beach. And what is 4? Alice and her husband were not together. Okay. Or Alice was in the bar and Alice's husband was on the beach. Yeah, that's actually what we decided. If Alice's husband was in the bar, the woman he was with was his daughter. The child who was alone was his son. And Alice and her brother were on the beach. Then either Alice or her brother was the victim. So the other was the killer. But from 5, the victim had a twin. And this twin was innocent. Okay? Since Alice and her brother could only be twin to each other, the situation is impossible. So they couldn't kill each other, Alice and her brother. Therefore, Alice's husband was not in the bar. So Alice was in the bar, right? And that's what we, right. So far, it's actually, so Alice was in the bar with her son. And the child who was alone was her daughter. Okay, look, it looks like, it's not me who solved it, it's you. I don't know who exactly, but bravo, yes, because I think I wouldn't solve it actually. It would be really. Okay. She was with her brother or her son. And we, Okay.
I don't understand why in the solution, since Alice and her brother could only be twins to each other, why children could not be twins to each other?
No, they could. You see, it was in previous reasoning. No. They just led it to contradiction, because you see, if they were twins, they could not kill each other. That's the thing.
Oh, okay. And one of the children were
Because
okay.
of this condition 5.
Mhm.
Yeah. So we conclude, we rule out this option. Okay. The victim could not be your husband because none of the others could be his twin. Okay. So the killer was her husband and her victim, and the victim was the child he was with. But this situation is impossible because it contradicts 6. Yeah, because killer is younger, right? Therefore, Alice was not with her brother in the bar. So Alice was with her son in the bar. Then the child was who was alone was her daughter. Therefore, Alice's husband was with Alice's brother on the beach. From previous reasoning, the victim could not be Alice's husband. Okay, so yeah, bravo. Yeah. So I didn't see actually who proposed the solution, but that's just right. Alice's brother was the victim, and Alice's husband was the killer. Yeah, that's yeah. Yeah. Let me just So who proposed the right solution? Okay, it was collective effort, of course, but I think some of you really was okay. So so it's done after all. Okay, thank you. It's done. It's done after all. Okay, let's see what kind of moral they want to. The argument relies on some extra logical elements. For example, that the father cannot be younger than his child, right? And that the parent and his or her child cannot be twins. That's true. But the argument also involves a number of common logical terms and associated patterns of inference. In the next section, blah, blah, yeah, exactly. And I think what we do, so we are going, okay, after the break already, we are going to study these rules. And then I think they also have a place where they show how this reasoning we did, say informally, how it can be codified by using these rules, okay? To that end, using the method of symbolic logic, we will introduce variables. Variables — это как переменные, то, что по-русски называется, да, как в алгебре x, y, там, a, b, to stand for fundamental statement of proposition. But differences, I think we already came across last week, that variables in logic, no, again, they can be used for different things, but we will use variables for propositions. So usually in mathematics, in the school algebra, variables are used for numbers, right? So assume that a, b, x, it's a particular number, or it can vary. It could be this number or that number, right? But now it's proposition, and basically that means, well, that actually means two things. More formally, it means that those variables only take two values, and those values are true or false, right? Because already we discussed that when we say prepositions, we may think about prepositions like husband killed, uncle, or whatever, right? But actually, more formally, we are only interested in truth values. So we don't have a formal means so far to, to convey meaning beyond truth value. So we basically interested in truth values. Okay, so that's sort of prepositions. And then we have these symbols we already discussed last week. They are called prepositional connectives, and they stand for logical operations which connect preposition and produce new prepositions. No, it's actually true about these first two, conjunction and disjunction, which are translated into natural languages like and or. All right. We also have this arrow, which is translated into English is just if then, but again it's binary in the sense that it kind of glues or connects two prepositions like A arrow B. A implies B, and this is a new preposition. And negation, it works differently because it's not binary. It does not connect two prepositions, but it modifies just one given preposition. So we may have some preposition A, and we may have its negation, not A, right? Like husband killed uncle, or it's not the case that husband killed uncle. So that's how negation works. All right. No, that's already described you that we are going to have this rules of inference, and above represented with the horizontal bar, and above the bar we have assumptions. So those could be kind of primitive assumptions, as in this 1, 2, 3, from 1 to 6 in our example, or they can be obtained from some earlier inferences, right? And below the bar, we have a conclusion. And then we actually discussed that we want to think about this conclusion as a logical consequence. So it is a syntactic device in a sense, it's kind of game of symbols, but the idea, of course, that this game of symbols somehow represents a reasoning, represents something, I would say, meaningful, which is a reasoning. Yeah, that's how it works. Okay, and now so we just turning. So again, we just look from particular rules, actually related to particular operations, and then with implication, conjunction, negation, blah blah, and then so we'll, after the break, we just go through that, and finally, we look once again how they are used in a proof. And finally we'll come, there'll be also some exercises. And it's actually next chapter is more or less the same, but a more formal manner. And and finally, it's, you see, page 19, we have a complete list of those rules. But I think pedagogically it would be better rather than we just start with this list, which looks a little bit like, hubris, a lot of formulas. We just start step by step introducing them, and only after that we kind of see complete list of those. Okay, so this is the plan for what we do after the break. Now I think it's good moment to make a break now, because it will be okay. Or please, if you have some questions, maybe about this stupid example or whatever. But very good. Yeah, that finally we resolved it. It's actually your contribution was better than mine, because I could remember, and I must confess I could see kind of immediately the answer. Maybe there is people for whom it's really easy to to see kind of immediately, but I'm certainly not one of these. Yeah. Okay. Now, if you don't have questions, let's make a break. So we start 18:30. Let's make half an hour break. Okay.
Okay.
Okay. Okay, let us resume. So let me again make some historical digression, say a couple of historical remarks about logic and more specifically this system of logic deduction system that we are going now to study. So I mentioned already, logic is of course a rather old discipline, maybe not as old as mathematics, and at least if we are talking about like European tradition, the history of logic is well traceable back to what we really may think of as a kind of beginning of logic. Mathematics does have really any like beginning, who was first mathematician, but in logic is there is more substance to say that actually first logician in anything like today's sense of logic was philosopher Aristotle. I think I already mentioned he has actually two works which are more stuff related to logic in Aristotle's writing, of course, but there is two specific writings which are called analytics, по-русски аналитики. It's called like first analytic and second analytic, or prior analytic and posterior analytic. And this posterior analytics is more, say, philosophical, it's more like epistemology, but this first analytic is actually a system of formal logic. Oh, I'm afraid I think my headphones are disconnected. Can you hear me? Okay, yeah, now it's maybe better. Yeah, but that's a long history, of course, right? Aristotle lived in the 4th century before the Christ, and then the history of logic is very, very interesting subject by itself, but we don't have really time to study it systematically. In so-called Middle Ages, logic was quite a popular subject, and it developed in form of commentaries to Aristotle's writings. Okay, it's again a long subject, but what we are doing is a bit more specific than this general logic, is what today is called mathematical logic. No, it's again the boundary between, say, mathematical logic and general logic is not absolutely clear cut, because some sort of symbolic methods are used in even most informal logic, and so it's in a sense it's a matter of degree how much mathematical is your logic. But let me share kind of father of mathematical logic in today's sense usually qualifies George Boole, who was a scientist, philosopher, mathematician of 19th century. Here is can you see the Wikipedia article?
Yes.
Mm-hmm. Yeah. So he published several books on logic, and one of these, probably the most popular, is called Laws of Thought, like законы мысли. Yeah. So he kind of applied in some cases interesting, in other cases more, we may say, superficially kind of mathematical methods which were already well developed at that time, say, to logic. No, today he's remembered because of Boolean algebra, Boolean structure. Probably I'll tell you a couple of things also later in our course about him. So that's 19th century. However, in the very end of 19th century and say beginning of 20th century, logic actually underwent a revolution. So it was really changed rather rapidly, abruptly. Now, of course, the same applies to many things like, arts, music, science, physics, right? So it was, and even political systems. So it was kind of time of revolutions at that time. So of course, what I teach you now, it's today's logic. I'm making these historical remarks, and I think that's a good idea to have at least some very minimal historical perspective. However, my task in this course is to teach you logic, which is today's logic, which does not mean, of course, kind of cutting edge research in logic, but at least logic in some modern form. No, by the way, of course, today logic is very vividly developing subjects, and particularly there are many interesting research somehow in between, say, logic and computer science. And our course, as I mentioned, even if we don't go really to computer science, it's actually close, right? So what I mentioned in the beginning of last lecture today about this proof assistant lean, right? So what we are going to study, this so-called system of natural deduction. So let me very briefly comment on that. So the kind of author, inventor of the system is a German mathematician, Gerhard Gentzen, who you see who died in 45. No, unfortunately, he died rather young. He was stupid enough to be involved in Nazi party, not very serious as far as I understand. He was not a kind of party boss, nothing like that, but he was member of the party. And actually he was taken as a prisoner of war, and he died starved of hunger in Soviet prison camp, you see, in Prague, when Soviet Union occupied Prague. And he was rather not very young. I think he was 40 or something. So that's of course unfortunate. On the other hand, he was not how say, innocent, quite fully innocent. But anyway, I just mentioned these details. Why? Because he's a teacher of Gerhard Gentzen. He's actually better known maybe internationally as a mathematician, not only a logician, but logician is particular. And this is very important figure in mathematics and mathematical logic in particular. His name is David Hilbert. You know, he died in 43, just in a rather serious age. You may calculate how old he was, 80 something, right? And he produced, he is enormously influential as a mathematician, actually in many fields of mathematics, but including mathematical logic. And so why I mentioned Hilbert, why I mentioned Gentzen, just to explain something that is commonly referred today as different styles of, say, of logical reasoning, if you like, right? So one is called Hilbert style for Hilbert. Hilbert style for David Hilbert, and the other called is Gentzen style. That something is not everybody knows, but you will know, but all logicians do know Gentzen style.
Sorry, we still see the browser.
Yeah, thank you. Yeah, Gentzen style. So I want just to explain you what is the difference. No, the difference roughly is how you represent, say, symbolically, mathematically, how you present laws of logic, right? Because if, as George Boole says, the laws of logic, that's of course very general, and then could be different ways to represent those laws mathematically. So Hilbert, basically, he tried to represent those laws in a form of, say, certain logical truths. No, I can give, which are otherwise also called tautologies. Да, по-русски тоже знаете слово тавтология. Tautology. No, as an example of tautology, I can give you actually a law of excluded middle, A or not A. And that's actually a controversial law, which not everybody accepts, but that we're going to discuss later. Now I just want to point it as a way of representing it. So you see, A here stands for, it is a prepositional variable, right? So stands for some preposition. And so what that says in natural language, that if you take some preposition and its negation, right, and take disjunction of these things, then it's always true. Yeah. So if A is true, no, if one of these disjuncts is true, the whole disjunct is true, right? And if A is false, in that case, non-A is true. Right. So you may also probably, so that's something which is always true, but if you write, if you replace, yeah, and that's called law of excluded middle. Sometimes it's abbreviated like LEM, law of excluded middle. And excluded middle, it's again, it's traditional medieval term for this, which roughly says that there is no something between A and non-A, that in that sense, excluded middle. But that's again, that's traditional name. But if you take, instead, if you replace disjunction by conjunction and write A and non-A, right? Yeah. Then you obtain something which is always false, and that's contradiction. And when I say always, why I say always, it's not about time, right? But it's just about the fact that this is a variable. So whatever A you take, it can be true proposition, false proposition, but this formula will still be, this will be always true in classical logic, right? Law excluded middle, and that one will be always false. Okay, so coming back to Hilbert and Kensen, and Hilbert tried to codify logic, if you like, in form of those tautologies, but then you still need the rule of inference, right? Because in logic, logic is about reasoning, and reasoning is about, how say, obtaining some new proposition from some given preposition, right? That you call assumption, and then you reason. No, that's as we did in this example. Right, so you need a certain rule anyway. You cannot just go with tautologies. But what Hilbert did, he just used actually one rule. Okay, I will describe it later, but it just had a lot of tautologies and only one rule. And then he managed to obtain all logical truths just by using one rule from these tautologies. So that was his project, if you like, right? However, Gensen, who was his assistant, so he was younger and was not his student. I think technically he was not his student, but was his assistant later. No, anyway, student in some, you know. pupil. Okay, so he learned logic from Hilbert. Yeah, and he argued that this is something unnatural. It's not like it's not kind of logic which is really well applicable to reasoning, whether it's mathematical reasoning or as in this example, right? Because in reasoning we really need rules. We don't use these tautologies. We use rules, right? We reason, we infer something from something, and every time it's certain rule that this reasoner follows. It very rarely comes to tautologies that may be interesting, I don't know, theoretically, mathematically, philosophically, whatever have you, but it's not how people reason. And that's exactly what's the reason why Gensen called his system natural. So he called it natural deduction. Or yeah, let's see how it's. By the way, I forgot how it's in German. Let's see. It should be there. No, that's Hilbert, and this is Gensen. Yeah, it was not in the name of his. Okay, I can look here and I can see German version, and yeah, naturalischen Schließen. Okay, yeah, that's so he somehow so this word natural actually refers to this argument that that's something which is better fits the standard practice somehow, right? So it's even if it's theoretical, it's also more practical than that. Gensen system, so that's the idea. And actually, more recently, it became very also popular in logic, also because of computers, you see, because if, of course, I think I already stressed that several times, that there is, of course, a gap between, say, logic, even mathematical formal logic, and, say, computer, right? What you implement on computer. It doesn't work immediately, it doesn't work absolutely smoothly. However, if you still want to implement certain system of logic on computer, it's rather obvious that you need rules, right, that you implement in form of, say, algorithm on computer, rather than those tautologies, right? So that also explains why these Gensen style systems, they are more recently became again somehow more popular, if you like, and more studied, and yeah, and that's also a reason why we do this in that course rather than studying, I don't know, Aristotle's syllogistic. Syllogistic is a name of Aristotle's system, and it's actually it has certain features which are similar, and there are ways also, if you like, to translate this old Aristotelian system into modern system, into modern setting. So there is some important continuity, of course. It's not like logic starts with Hilbert or with Gensen. That's absurd, of course, would be absurd to say this. Nevertheless, there are also these nuances. So, so one special reason why we specifically interested in this Gensen style system, well, one thing we can really take seriously, I guess, this argument that Gensen himself put forward, right, that it's more natural in the sense of being more practical, if you like. And there is a further argument, something that Gensen, I don't think, had in mind, even if he could, because there were people already around like Church, like Turing, and Hilbert, by the way, was well aware, so he was thinking about everything. So today we may also add to this general argument about this naturalness of this rule-based system. Also argument that it better serves computer science, right? It allows for more easier or natural, if you like, implementation on computer. So I can write here something like many axioms, and by axioms I now understand actually those tautologies, and I write few rules. And here I just write many rules. And axioms basically are not needed, maybe not needed at all, and we'll see. So this system of natural deduction in original form, it doesn't involve anything like this tautology. We simply don't need them there. So many rules. This is, of course, again, kind of informal distinction, but useful and important. Okay, let me now we go back to my PDF, and now we sorry. Okay. Okay. Yeah. So we go to those rules of inference. Now again, remember I told already, when we call those rules of inference, this is something semantical, right? We really think about this because inference is a logical concept, one of central logical concepts, and more syntactically, someone say more formally, we may also call this inference, we may call it deduction, and in some cases also derivation. Derivation is just syntactic. It's how we obtain new symbolic expressions from some given expressions. No, okay, those nuances are not very important. So we start with arguably the most important rule. No, even it's not straightforward how you say what is important, what is less. It's not very, I'll say, well-grounded such judgments. But that's actually a rule that Hilbert also used, and it's called by traditional name Modus Ponens. Yeah, so that's something that comes again from some medieval textbooks. But okay, I will simply use some traditional names without talking about history any more. So it's called okay. So what we are going to study, it's natural deduction. Natural deduction, which once again just a system of rules, and actually it's in a certain sense it's complete system. You may also remember what I told you last time about semantic completeness. Remember, soundness and completeness, and that system that we are not going to prove, because this would require kind of more than we can do. However, it's important to understand that complete means that we may derive from no assumption every tautology in this system. Sometimes it's abbreviated as ND, natural deduction. And so now I just introduce rule after rule and we discuss them, and maybe next week I think we just come to full complete system of rules and think about it as a whole. At that point we just consider rule by rule, so to speak. Okay. Yeah, so our first rule is called, which is also used by Hilbert, that actually was the only rule he used, is called Modus Ponens, traditionally. Ponens? No, in modus is a scheme, or how do you translate it? Ponens means to put something, right? But here what is put is a preposition, basically. Okay. But that name, yeah, that's often is abbreviated like MP, Modus Ponens. Yeah. So this rule has two assumptions and one conclusion, and it uses two variables. So we have a and B as a prepositional variables. So they stand for preposition prob variables. Yeah. So first assumption for this rule is just A. Okay. Second assumption, yeah, I should say sometimes people use commas and sometimes they don't use anything. I think I'm not going to use anything. Just, but it's important to somehow distinguish one expression from another expression. But I think it's okay. I just take sufficient distance. So one is A, and second is A implies B, right? And we discussed with you implications already, right? On semantic level, we wrote a truth table for implication. So now it's actually a very good point to see clear the difference between implication and rules of inference, right? Because we say A implies B, but by itself it's not inference. That's important to understand, right? A implies B, it's another proposition. If A, then B, like this, right? And probably you can guess what is conclusion, what you can derive from such assumptions. No, maybe let's take some example. Who can just give me some example of A implies B? So it should be just any preposition of form A implies B. No, actually, I want not just any preposition, right? I want actually true preposition A implies B. Right? Just give me example of true preposition A implies B. So it should be like this: if blah blah blah, then blah blah blah. Yeah, and this, by the way, is called antecedent. I think I told you already, but let's again, if we have this A implies B, this is called antecedent. Ante in Latin means before. Antecedent, something that comes before B. Antecedent, right? And this is called consequent. It's, of course, it's related to logical consequence, to inference, and that's now we see how exactly it's related. Consequent. Like this. If I don't know, Peter, we don't have, is a student. What it implies to be a student, you should know this better than me. Is a student. We'll say in small name, maybe for being right. Then he I don't know, must take course D or C or how it's take a course in logic, for example. He takes, yeah. So A here is Peter is a student in Smolny. This is our A, and he, we means Peter, takes a course in logic. This is our B. Okay. And so we say if Peter is a student of Story, then he takes a course in logic. Okay. Okay, let's just take this example. Probably I should say you that, remember we discussed truth table for implication. Now let us recall. Let me write it here how it works. So if I have my A, and here I have my B, and here I have A implies B, right? And then I'm making a little table. So it could be both true, or can be true, false, or can be false, true, and can be false and false. So what should I write here?
So if both are true, then the implication is also true.
Yes. What about this? And what about these? Or probably we didn't discuss this. I just can't quite remember.
No, we discussed it would be false in every other.
No.
No?
No. It's false actually only here. And this is true and true. Yeah. And you see, in a sense, that's conventional. You may say this is counterintuitive. No, this is okay. Intuitive both are true, right? No, why here you have false? No, the idea somehow is that if your antecedent is true, consequence should be also true. So even if it's not a rule of inference, it's still some idea of truth preserving, if you like, right? Of inference. It's some idea of truth preserving. So you see, T is true and A is true and B is true. However, if you have a situation where A is true but B is false, then there is no implication, so to speak. Yes, then implication is false. Yeah, it's more difficult to explain, if you like, just intuitively, what happens when antecedent is false. But here the intuition is that actually if your antecedent is false, then everything follows. Yeah, so it's not quite the case, but it's related, say, to principle. I think I also already mentioned some times ago that is called by a Latin name as falsio quod libet. From falsity, anything. Из лжи что угодно. You see? No, you may think about this as a convention. However, if you really think more how this whole system of logic is constructed, you see that that is, say, a natural thing to assume about implication, right? So once again, if antecedent is false, then whatever is your consequent, whether the consequent is true or consequent is false, your implication is true. You see? Right. And by the way, this is the reason why this implication sometimes is called also material implication. Material implication. And that's actually material implication. No, material is just description. So you may say just implication, and this is the same that material. So it's not specification that some implication is material and another, I don't know, immaterial. No. But material refer to the following fact. You see, I got that example. No, okay, we may say it's more or less natural, right? If you are a student, you have, I don't know, certain duties, whatever, or it implies something to be a student, implies you do this or that and don't do this or that, and so on, right? However, you may also think about kind of stupid examples, like if I am a Martian, no, assume that it's false, right? Then 2 times 2 equals, say, 5 or 4 or 5, yes? And that will be true. Or you may just take 2 truths. If I am 57 years old, that consider this example. If I am 57 years old, then 2 times 2 is 4, right? And so you have this distance. The antecedent is true about myself, and consequences true, yes, but they have nothing to do with each other. So It's not because I'm 57 years old that 2 times 2 is 4, right? You may say this is because I'm student in Smolny that I want that I need to take a course in logic. So there is something which is actually in logic called relevance. Relevantness, relevance. Relevance means that two things are semantically connected. So you may probably say that this first antecedent is explains or provides some reason why the consequence is true. Okay. However, this can be part of your implication, but not necessarily so. So so this material implication simply does not distinguish between examples like this, where there is certain relevance, to example like that, right? I'm 57 years old, then 2 times 2 is 4, or Volga falls into Caspian Sea or something, right? So there is no relevance here. In logic, people develop so-called relevant logics, where they try to take into consideration on formal level this relevance. However, this more simple logic, basic logic that we study, it does not take relevance into consideration, and that's why this implication is called material, you see. So you should not, if you like, expect too much of implication. It's how to say, it's more stupid than you can kind of imagine using that sort of examples, right? Just okay, but that's implication. And once again, implication is another proposition. So just like you have connectives such as conjunction and disjunction, you also have such connection as implication. Okay, and by itself it does not constitute any inference. So if I'm saying, if I'm 57, blah 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 blah, 2 times 4 is 4, you don't deduce this 2 times 2 is 4 from the fact that I'm 57 years old. Okay. And of course in other cases, so to do some inference with using application, you still need a certain rule, you need something. And that's exactly what this Modus Ponens serves for. The idea is this, that if you kind of grant, no, if you like, I can talk in terms of truth values, but I also may talk in terms of kind of grounding, granting, some sort of epistemic concepts, right? So if, no, let's do simpler in terms of just truth values, right? So if A is true, like here, right, and B is true, so you have A is true and implication is true, and implication is true. So you see, if I say A is true, that means that I rule out these two cases, these last cases, right? So I'm saying antecedent, my A is true, and consequent, yeah, and I don't know yet about consequent, but I know about implication. So A is true, implication is true. Since A is true, these two last cases are ruled out, right? So what remains, this is first thing. And so what I may conclude, it's actually B. Yeah. So this is a modus ponens. If I have A as an assumption and I know that A implies B, then I conclude B. That's the thing. No, just using our example, if Peter is a student in Smolny, then he takes a course in logic, right? Yeah. But I may not know whether Peter is a student or Smolny or not student in Smolny, right? Now, if I want to make really conclusion, not just implication, but conclusion. So I grant that Peter is a student of Simon, okay? And let's say our implication is granted. So I really need these two assumptions, not just one. Or there is another also word, it's called premises. So in singular, it's one premise. It's actually all the term which comes from, again, Aristotle's syllogistics. Yeah, premises, yeah, I think. They don't do it like in Greek. Premises. Yeah, in Greek you would need to say premise, like hypothesis. Okay. Yeah, so that's modus ponens. Of course, you can also use it in kind of a stupid way, saying I am 57 years old, and then you have this implication, and then you conclude that 2 times 2 is 4, and say if you don't bring in any, say, epistemic consideration, you may say this is a valid inference, right? It preserves truth, it's accords with modus ponens, but of course, epistemically, so in terms of knowledge, it just absorbed, right? Because it somehow suggests that you somehow prove that 2 times 2 is 4, using as a premise that I'm 57 years old, and this implication. But that's, of course, it doesn't explain anything. It doesn't provide a proof that 2 times 2 is 4, right? Yeah, that's actually good remark. It just shows that this theory that we are going to develop, it's kind of incomplete. Not incomplete in semantic sense, but incomplete in that it kind of captures something important from how we reason, but very far from being sufficient, if you like, right? Because you may still invent a reasoning which accords with those rules, so there is no contradiction, but from epistemic point of view, it's kind of absurd, right? It's not absurd in terms of contradiction, so it's kind of legal, okay, but or valid, but it's not epistemically valid, right? It's because if we really want these inferences be proofs, right, that's certainly not the case. We cannot call it a proof of 2 times 2 is 4 that I'm 57 years old. That's absurd. No, I don't know. Just please ask me if something is not clear about modus ponens. It's very basic thing. We will also look what those authors say about that. Yeah, they give it another name, implication elimination, but that's, I should say, it's a rather technical name, which is only used in this Gensen style systems. So you see the author want to pretend that it's kind of on equal footing, those names, but they are not on equal footing, of course, because that's a very traditional name. Of course, in traditionally it could be given in slightly different forms, and so we are not going now into history. But implication elimination just refers to basically to natural deduction. But that means that you had this implication, and here it's no longer there, right? So you eliminate it. That's the idea. Yeah. Yeah, it's also, you see, they change the order of premises, but that's not essential. The order is actually we suppose that these assumptions could be permuted as you like. So it's not ordered list, actually. You just put them up there in any order that you like. Yeah, no, here is example just based on this problem that we so brilliantly solved. That's rather you, not me. If Alice was in the bar, Alice was with her brother or her son, right? First assumption, and you see it has this form of implication, right? Second assumption, Alice was in the bar, okay? Now we conclude Alice was with her brother or son. You see, it may look very trivial, very primitive. So you may argue there is no reasoning here, right? It's all immediately clear somehow, right? That but that's how logic works. You see, it's in logic we need distinguished, very basic, very elementary steps, and then build more complicated reasoning, more interesting reasoning from these primitive things. And as I say, Modus Ponens is one of those things. Yeah. No, I don't know if it's easily understood or there is some difficulty here. No, may I, okay, let me just ask maybe you for some other example of Modus Ponens, so you somehow feel better how it works. You just give me any example, smart or stupid, whatever.
I have a stupid example.
Okay.
So if it's raining outside, then the road is wet.
Then the road is
Wet.
wet. Okay. It's implication. No. Look, now it's about what you gave me. It's example of proposition, right? Of this form, A implies B, but it's not Modus Ponens. That's very important. You see, what I want you, I see they somehow close, right? They collide, but it's very important to distinguish between just a proposition, which has this complex form, right? Which can be analyzed into antecedent, consequent, and implication, right? But that's still a proposition. It's not Modus Ponens. Okay. So let's now use this proposition to give example of Modus Ponens. So, okay, let me probably write it down. So, if it is raining raining outside, then the road is wet. The road is wet. Okay, so we have I can picture the kind of logical form of this proposition as so let A be it is raining outside, right? And the road is wet is our B. And this if then correspond to the zero, which is implication. Right? So what we have this thing. A implies B. Okay. And now let us use it for modus ponens. But then you need to say a bit more. Now, roughly, if we somehow think that everything is relevant, right? So we are taking kind of good examples as you provide. That's good example, right? Because road becomes wet because of rain, obviously, right? Not because of something. Okay, so let's say that's good example. But now, since it's good example, say I don't know it's raining or it's not raining. Okay. So I know that whenever it rains, the road is wet. Okay, but I don't know it rains or not, and I don't know the road is wet or not wet. So you see.
So I need to say that A is true, and
yeah, the road
implication
it's raining, right?
Yeah, it's raining, and the implication is true, and from that I can derive that B is also true.
Yeah, exactly. So you may derive that since it's raining, and that you making like separate judgment about raining, right? This is one thing, but then you need to state A separately. That's very important. And then you're in a position to conclude that B. Yeah. And that's modus ponens. Actually, traditionally, that's something that it's not system of standard natural deduction, but I think if I can remember, they also use modus. It was called modus tollens, and frankly, I forgot what tollens in Latin means. You may look into dictionary. I think a modus tollens works like this, if I remember correctly. Now you have also A implies B, but then you have not B. Okay, is it correct or not that I can derive? I can infer from that. I think not A, right? Is it correct or not? No, we may actually look into this truth table. I think that's modus tollens. If I'm not making a horrible mistake, no. A implies B, okay, that's the same. Right, if I simply saying non-A, right, I cannot conclude anything about B, because if I have not A, implication is true, and B may be true and may be false. But if I have not B, and this is still true, yeah, here we had this, right? If I have not B, yeah, so it's only here. Sorry, no. I might have not B, I may have here and here, right? Maybe not B. And A. Yeah. Sorry, let me check. I think I'm right, but oh, sorry. Modus Tollens. If P, then Q, then not Q, therefore not right. Right. That's correct. That's if the dog detects an intruder, the dog will bark. The dog didn't bark. Therefore, no intruder was detected by the dog. So that's kind of thing. Okay, and let's come later to the question how we may justify this modus tollens. Of course, even if it's not a system, a part of the system in natural deduction, so it's not a basic rule, but actually it's a derived rule, so we may actually derive it. But let's do it later as an exercise. Okay, P, Q, non-Q, non-P, right. No, I just mentioned this modus tollens. I don't know, also for historical reason, but to let you understand how it works in logic. But actually, the specific thing of natural deduction that after modus ponens, what we introduce, it's not modus tollens or something like that, but we introduce kind of a dual rule for introducing implication. You see, so that rule eliminates implication, and the dual rule or complementary rule, if you like, right, it introduces implication. So here we have this idea that we have rules for introducing connectives and kind of complementary rule that eliminate them. And there is a kind of harmony between the two. And actually this harmony, it's even technical concept, but we'll not go that far. Okay. Can you see now PDF?
Yes.
Yeah, okay. So that was called otherwise implication elimination, traditionally modus ponens. And now we have another rule for introducing implication. Let us see. So now we won't derive implication from something else. And now they want us again, use this story, this murder again as a source of motivations or examples. Consider the beginning of the third paragraph, which argues that if Alice's husband was in the bar, then Alice or her brother was the victim. Abstracting away some of the details, argument has the following form. Suppose Alice's husband was in the bar, then blah, blah, then Alice or her brother was the victim. So this is what is called hypothetical reasoning. So we introduce certain hypotheses, right? Like suppose this and that, which is compatible with, no, at least which appears to be compatible, right? Because certain hypotheses we introduced, but then we derived contradictions, so we ruled them out. But they appeared as if we could, it was a possibility. Even after reasoning, we could see that is not really a possibility. Right, and this is very important. So let's see how it works formally. And that's already, if modus ponens is, as I say, is a very traditional thing, is comes back, if not to Aristotle, to somehow close to Aristotle, maybe even Aristotle, I'm not sure. But if we want this dual rule, this is already something really specific for this approach invented by Gerhard Gensen. And that works like this. So we have this hypothesis, say A, and then, okay, we reason, actually here we may apply some further rules, which we are going to specify later, you see, so it's kind of dotted rule. And dotted means that we may fill these dots with some other rules, which, so in that sense, actually those rules, and they are all schematic, and they're schematic in the sense that we may, they may give different values to our propositional variables, but not only that, you see, they're also schematic in the sense that we may fill such dots with some other rules. So the idea here is this, that we take a hypothesis and then we reason using this hypothesis as an assumption, you see? And of course, our reasoning, we may say, depends on that hypothesis, right? So we, if we want really to conclude B and say believe B, right? We should also believe A, because if we simply drop this assumption, well, it depends, of course, how we reason in between, but generally, of course, we use this hypothesis, right? So we are saying that if Alice's husband was in the bar, then such and such thing happened. So all this reasoning just is with this assumption, which has this hypothetical nature, right? It's not given to us as a data. It was not part of our problem. It wasn't our hypothesis. However, what we can do, suppose we use this hypothesis, we infer B somehow, but what we now can do is the special step is introduce implication. So we might still not decide whether actually A is true or false, right? But what we can do, we can replace this reasoning from A to B by implication. And what is important, that implication does not depend on A in the same sense, you see? So implication would be true even if A is false. That's the thing. Now, remember how we reasoned. Alice's husband was in the bar, right? And then we conclude that he was on the beach, not in the bar. But if he was in the bar, I already forgot the example, then two kids were in the beach or something else, right? No, at least we may say, okay, if he was in the bar, he was not on the beach. Okay, that's file safe, right? So we may conclude from this hypothesis that that he was not on the beach, okay? And we still don't know whether his hypothesis is true or not. However, if we simply say, if the husband was in the bar, then he was not on the beach, right? And this is implication. And this is true anyway, whether A itself is true or not. That's the idea. And you see what's going on here. First of all, it's called implication introduction. Yeah, you see, and symbolically they write Modus Ponens. This is a sign, a symbol for implication, and E, big E, stands for elimination. And here we have the same implication, and big I, that stands for introduction. And a very important concept of this natural deduction is so-called discharging hypothesis. They say cancel. It's actually usually called discharge. Ну, по-русски как-то мы скажем отменить, например, да? And that's correspond to the idea that this reasoning with dots, right? It's based on this hypothesis. However, when we do this step, we introduce implication, we no longer depend on that hypothesis. So we still have this A, but it's no longer assumption. It's just a antecedent in the implication, but antecedent is not assumption, right? And so we may use this implication as an assumption, but it's if this dotted reasoning was made according to rules, implication is true anyway. You see, so if you like, we might not know any truth in the beginning, right? And still, if we reason correctly, we finally come to something which is true, and this is implication. That's interesting, right? So it's kind of logical way to produce truth, if you like, right? No.
Sorry, but are you writing anything right now? Because I still see the previous page.
No, I just was showing what you. I'm showing the textbook.
Oh.
No.
No.
Yeah, that's why I asked. Okay. No, this one.
Yes, now we see it.
So once again, we had this modus ponens, otherwise called implication elimination in natural deduction, right? And that's how it works, we already discussed. And we have kind of complementary thing. Here we eliminated implication, right? So above the bar, we have implication, and below the bar, we don't have. And here is the other way around. Above the bar, we don't have implication. Below the bar, we do have implication. And once again, what we have above the bar, we have kind of hypothetical reasoning from assumption, but that may call it hypothesis in this concept, A, right? And we infer certain B from A without really knowing whether A is true or not. However, we may conclude A implies B, and that would be our conclusion. If we reason here correctly from A to B, even if we still don't know anything about A, but we do know now that implication is true, whether or not A is true. And that's the fact that we no longer depend on this hypothesis, assumption, is marked on this diagram by this little horizontal bar. And it's called discharging hypothesis or cancel. I probably may. Okay, let me also probably write it once again here. So this thing, modus ponens, we are going also to call implication elimination, right? Elimination. And then we have a complementary rule, which is schematic, which is kind of heavily schematic, and which is like this. We just take this A as a hypothesis. Let's assume that A and see what follows, roughly like this, right? And then we reason, and here we need to specify, and we are going to specify in the next week, what we can and what we cannot do here. But suppose we reason, say, correctly and infer certain B from this, right? At that point, we may apply a new rule, which is complementary to Modus Ponens, and that we are going to call it implication. No, instead of implication, I'm just writing a little arrow, introduction. Intro. Okay. And I obtain implication, A implies B, right? And very importantly, I discharge my A.
We still see the textbook.
Sorry, I already wrote so many. Оно как-то иногда перескакивает, я вот не пойму, как это. Иногда мне надо вот каждый раз все это менять. Okay. Yeah, here I just added this another name, implication elimination. And now, okay, I take A hypothesis, I infer B according to other rules, and then I use the rule that I'm describing now. That is, I introduce, instead, I kind of replace this reasoning by implication. So actually these two rules, Modus Ponens and implication introduction, they show the the relationship between implication on the one hand and the relevant rules of inference. And actually there are two such rules, right? One, Modus Ponens, obviously we discussed, but there is also another which is kind of complementary, symmetric, if you like, which just works the other way around, if you like, right? So then we had we eliminated this thing and obtained B, and now we introduce it, right? So we introduce, but very importantly, we discharge hypothesis. Or cancel. So your reasoning was dependent on this hypothesis about which you could not be sure, so to speak, right? But using this rule, you now discharge it. So you may use just that implication as an assumption for some further reasoning. And now it does not depend already on hypothesis, your implication. You can just be sure that it is true. Well, you still don't know whether A is true or not, but you do know if this dots is done correctly. So you do know that A implies B is true. That's the idea, but we'll see it in further examples, actually, how it works, discharging hypothesis. Okay, please ask me if there are questions. No, if not, we may probably just learn one more pair of rules, and then we continue next week briefly what we can do about conjunction. Okay, let's do it briefly because this, I think, it's somehow simpler. So again, the same logic, if you like, right? So we have a introduction rule and elimination rule. That time we are going to start with it. I think they started with elimination rule only because Modus Ponens is kind of so famous and known far outside this particular logical theory. right? But more natural logic, if order is start with introduction rule and then look into elimination rules. So introduction rule for conjunction is just that. So you have A and you have B, and above the bar, right? Those, so A and B are your assumptions, and as a conclusion, you obtain A and B. Now, again, it may sound just completely tautological somehow, right? But once again, that's how logic works, you see? So since you have separately these assumptions A and B, you are entitled to connect them by conjunction. And that's, if you like, it's a way to say how conjunction works, avoiding truth tables, right? Because we had the truth table for conjunction, that was semantic, and that is a kind of syntactic. No, at least it's a different way to think about conjunction, right? So we have just A and B, so we connect them by conjunction.
I'm sorry again, but are we supposed to see a screen?
Yes. But that, look, but that time I certainly. Do you see the screen?
Yeah, I see the textbook.
Yes, right, and that's
Okay.
what. No, now it's okay. Yeah. Now here we have it. I'm not sure I can. It would be nice if I can just draw on this. Yeah, I probably could do. Yeah, this is introduction rule for conjunction. Okay. Yeah, I can. I don't just make it. Yeah, that way. Yeah. Yeah. No, I think linguistic examples kind of useless in that case because it just would be saying, okay, Alice's husband was in the bar and Alice was on the beach. No. Alice's husband was the killer. No, that's yeah, I think they simply don't give us linguistic examples because linguistically you're just saying two things and then again you say two things. But formally, of course, there is difference because above the bar we just have these propositions as two separate propositions, right? And below the bar we have a new proposition composed of those two. And this is, of course, not the same thing. So we have two propositions above the bar and one complex, but one single proposition below the bar. So in that sense, the rule, of course, is not trivial. This is an introduction. However, eliminations rule actually are two. So if you have conjunction A and B, you may infer A and you may infer B, right? Alice's husband was in the bar, Alice was on the beach, you infer that Alice was on the beach and you infer that Alice's husband was at the bar. Now, once again, linguistically, it may seem just kind of pointless. I think there is English expression like splitting a hair or something like that, да? Как это, знаете, расщеплять волосы. But logically, formally, it makes a lot of sense. And I hopefully will illustrate it with some further examples, right? And it's important that we have here two eliminations rule, not just one. Because you see, those rules are supposed to be syntactic. And that means that if you have A and B, we cannot simply permute this A and B. So you can take first conjunct as a conclusion or second conjunct as a conclusion. And that's not the same thing. Yeah, that's how it works for conjunction. No, and we'll see how it works for that's actually going to be interesting with negation, falsity. That's something that we used in our example, right? We tried some hypothesis and then came to contradiction, like here. And on the basis of this contradiction, we concluded that our hypothesis was false. All right, so we concluded non-A. Yeah, and that's something actually interesting and related to law of excluded middle, as we'll see. Okay, I think I stop here. So if we have some questions or comments. Yeah. So after next week, I think we finish all these rules and discuss also them, and then will be some exercise. So I'll ask you to prove, to deduce in the system certain things. It's kind of fun to make exercises. All right, and okay, and then we probably move to another formal system, which is more related to computation and the kind of ultimate idea, but I don't think I may really realize it in that course, is to show how this formal reasoning combines with computation. You see, that's why this proof assistance. So those of you who really get interested will be able to take another course for next year. I hope then we could do more stuff with real computer programming. Yeah. Ну, тогда, наверное, если нет вопросов, будем заканчивать. Или, пожалуйста, кто-то может еще что-то хочет сказать или спросить. Окей, если нет, то всем хорошей недели. Даже меня не видно. Да. Все, и тогда до скорого, до следующей недели. Всего хорошего.
Спасибо. До свидания.